today we will talk about other applications of the transistors, because so far we have discussed how to use the transistor for temperature compensation, how to use the transistor to drive the load, etc. we have discussed. Today we will look into the linear power supply and see how to use the transistors in series and parallel to push the power and then to push the voltage requirement. Similarly, we also discussed about how to use the MOSFET today instead of transistor in different applications like linear power supply and so on. So, first let us take how to use the transistors in parallel. So, transistors in parallel. Because if you want to increase the power capacity, then it is essential to increase the put the transistors in parallel. Let us take a typical linear power supply and then see how we can do this. So, in a typical linear power supply we have the transformer and then the rectified voltage of the transformer. We have taken this. So, we are rectified voltage of the transformer is coming here, and that actually we want to regulate. So, this we already discussed. So, we get unregulated DC here, and then to regulate this we have done put a error amplifier, and we had given the feedback, and this is connected to reference voltage, and then we have connected this output to this, and then we invariably connect the output on capacitor to avoid oscillations. So, this is coming as a V output. This is a typical voltage regulator that is used in regulating the linear voltage, in regulating the DC voltage. So, the unregulated DC voltage whatever is here, that unregulated DC voltage whatever is here, that appears as a regulated voltage at this point. Now, that is regulated against the reference voltage. For example, the reference voltage is 5, then we know this also has to be 5, and for example, if this voltage resistance are equal, for example, it is 10k and 10k per port, then if this is 5 volt, then we know this has to come to 5 volt. If this point goes more than 5, then automatically output comes down, and then that is followed here, then this output comes down, and then this output also comes down. If this voltage goes down, and if this also goes down below 5 volt, then this voltage goes up and output also goes up. That is how it is regulating. This we are already discussed in our earlier class. Now, our focus here is how to select this transistor, how to use them in parallel. For example, if I want to use for high power, for example, if I want output load here. So, suppose in this case, if it is 10 volt here, and if I put 1 ohm resistance, then I need to have 10 ampere current flowing through this. Now, the 10 ampere current have to go through this transistor. Then power dissipation on this transistor would be that I output into voltage drop across the transistor. So, if this is output, if the input is 15 volt, if the output is 10 volt, then you have 5 volt across this, and 10 ampere current flowing will create a 50 watts watts dissipation. So, this will be 10 ampere and 5 volt drop, that will give you 50 watts dissipation, and we have already seen earlier that kind of power dissipation will take the junction temperature to very high value, because junction temperature determines the life of the transistor, and reliability of the instrument again depends very much on power supply, and particularly the life of this transistor decides eventually the life of the equipment. So, one have to make sure that the temperature of the junction temperature of this is normally not going more than 80-90 degree to get long life. In that case, even putting a heat sink will not be enough, because that will demand very high heat sink, or even the high heat sink also many times not enough, because the if 50 watts is dissipated, for example, if we take 3055 for 3055 transistor, for 3055 transistor, theta between junction to case, that is junction to case, it is 1.5 degree C per watt. That is 1.5 degree reference temperature required between junction and case to dissipate 1 watt of heat. That is, from junction, if the heat come to the case, this is the case and this is a junction, if 1 watt heat have to come out, then the difference required is 1.5 degree. So, if 50 watt dissipation, then we need 75 degree difference in temperature between junction and case. If the case itself at 50 degree, then junction automatically will go 75 degree above this, that will take it to 125 degree, that will make the life of the transistor very short. So, in many cases it is not possible, even with the heat sink it is not possible to achieve required junction temperature. If you see here, we have taken the case of the transistor as 50 degree C. To keep the case of the transistor 50 degree, we have to have a bigger heat sink, because normally ambient itself goes many times more than 50 degree. For example, if the industrial grade equipment, the ambient itself to be considered as 85 degree. 85 degree C. So, it is very much essential to have transistors in parallel in terms of heat dissipation also, rather than current flowing through that. So, how to connect the transistors in series in parallel to reduce the heat dissipation as well as to share the current. Now, we can do that by connecting for example, two transistors connected here, the collector and collector can be joined, and then the emitters are joined through a resistance rather than shorting them directly, and then we join the bases together, and then this can be connected to the error amplifier, or it can be even driven through a Darlington pair. So, that is a V input, that is a V output, and then this is actually driven by the output of the amplifier, and the rest of the circuit is similar to what we have discussed so far. So, you connect the feedback here and the output here. So, here we have connected the two transistors T1 and T2 in parallel, and only thing is we have put two resistors equal values R and R in the emitter circuit to balance the current. These two resistors are actually to make the currents in T1 and T2. So, this current must be equal to this current. To make them equal only, these two resistors are added. So, this is essential point that one have to understand in connecting the transistors. Without these two resistors, then current sharing will not be assured. This is because if I connect them, for example, if I connect them directly in parallel without having the emitter resistance, then you have this arrangement. So, we put the V input here, and then we get the V output. Now, in this case, this is actually not acceptable circuit, because the bases are at the same potential, emitters are at the same potential, collectors are at the same potential. So, both the transistors will have same base emitter voltage. This transistor base emitter voltage is same as this base emitter voltage, equal to this base emitter voltage. But then if you look at the characteristics of the transistors, that base emitter voltage there will be a difference, because the for the same current, collector current, what is the required base emitter voltage for this and this, there will be a difference. That difference goes up to a maximum of 50 millivolt. So, for the same current, for the same IC, for the same IC collector current, VBE requirement is different. Is different for different transistors. This difference is nearly 50 millivolt maximum difference. This difference is 50 millivolt maximum. That means we have to somehow take care of this 50 millivolt difference to make the current more or less equal. For that purpose only, when we are connecting them in parallel, we are adding the two resistors and the emitter equal values. So, that is what we are doing. So, we take this and connect the two resistors at the emitter, and then collectors can be joined. Now, the bases can be joined. Now, we know that the difference of 50 millivolt maximum exists between this base emitter and this base emitter. So, if I add these two resistors, now the voltage at this point and at this point are same. That means VBE 1 plus R, I will call this as R, this is also R, I call this as X1, this voltage X2, X1 must be equal to VBE 2, this is transistor 2, this is 1 plus X2. So, if the difference between VBE 1 and VBE 2 are 50 millivolt, if VBE 1 and VBE 2 are differ by 50 millivolt, then X1 minus X2 will be 50 millivolt, or rather X1 minus difference S millivolt. So, the if the resistance are, if X R1 R is equal to 1 ohm, then delta I, current difference between them, current difference, because current of X1, then I can write that R into I1 plus R into I2 has to be 50 difference between R 50 millivolt. That will make, since R is equal to in this case 1, then I1 and I2 has to differ only by 50 millivolt. I1 minus I2 difference will be only 50 milliamps. So, the current can be current difference is maintained within 50 milliampere, that is good enough. If I increase the resistance of R, then even the current difference can be, for example, if I put R is equal to 2 ohms, then the difference will become 25 milliamps. So, one can select R such that the acceptable difference is maintained, but the 50 milliampere difference in 1 ampere current is more than enough for the normal applications. So, any number of transistors can be connected in series by adding the required emitter resistance to each transistor. Now, let us see how to connect the transistors in series. So, we have seen so far how to connect them in parallel to share the current. Now, let us see how to connect the transistors in series to boost the voltage. So, transistors in series. Now, let us take again the linear power supply example that we have. For example, we have assume that we need to have high voltage power supply Then our regular rectifier circuit is here. Assume I have a 1000 volt supply and I need only very low current, that 1000 volt regulated voltage I need. In that case, how will I go about designing this circuit? For example, if it is high voltage power supply, I will actually connect the transistor like this. Then you have the output, and then to get a high voltage supply, then I have to reverse the design. So, I have this, then you have error amplifier. Of course, to limit the current, I put the to make sure that the loop is stable. So, I put on empty resistance here. I will explain about this little later, that we give the feedback. So, in this case it is connected to plus and the minus is given to V reference. I give this one to V reference. So, the supply maybe it can be taken from here, or it can be taken from a low voltage supply if it is available, because that we anyway have to give to this transistor. So, the low this can be fed from the low voltage supply rather than from here. So, I take this output, then I connect this, maybe a low voltage winding that is provided in the transformer can help you to power up the Zener and operational amplifier. So, this is a 5 volt Zener and we want a 1000 volt DC here. So, we have a output capacitor connected here to stabilize the loop. So, if we take this circuit, this is a voltage regulator. It is a conventional linear regulator only. There is not much difference, except that we have put on this one is put in the reverse form, and we have also put on inverting transistor here to make it as a voltage regulator. Now, if we see analyze the circuit how it is working, see the this point is kept at 5. So, obviously, this also had to be 5. So, if the output voltage goes higher, then this voltage also will go high. If this goes high, then this output voltage will go high. The increase in voltage make this transistor to conduct more. This transistor conduct more, that current actually comes from here. So, more current will flow through this. So, if the voltage increases here, more current will flow through this. So, the more current flowing through this, will develop a more voltage drop. So, if you look at the voltage at this point, voltage at this point decreases when the current through this increases, because if this is 1000 volt and if it is 100 volt drop, then you will get 900 volt. If more current flows through this, then more voltage drop will be here and you will get only less voltage here. So, eventually if this voltage increases, so this voltage increases, that increases the current through this, that increases the current through this, and that will decrease the voltage at this point, and you will also get less voltage. If the voltage at this point comes down, then voltage at this point also will come down, and current flowing through this will decrease, and current flowing through this will decrease and make this voltage to go up, and the output voltage also will go up. So, that is how the regulator works, and makes it, if this is at 5 volt, if this is at 5 volt, then this is also will be at 5 volt. So, if I have for example 1k and 1k, then if I have 200k resistance here, then I will have approximately 1000 volt at this point, because 5 volt across this, and automatically 200 times, that is 1000 volt across this, and then you get 1500 volt. Normally we do not put on single resistance per 1000 volt. To limit the voltage rating, we put 3 or 4 resistance, such that the voltage rating is not exceeded, because the resistors have voltage rating as well as power rating. even if power rating is not exceeded, if the voltage rating exceeds, the resistors can break down, and then it will act like a short, and then that will damage the IC, and the regulator also not going to work. So, we may have to put normally about 250 volt is what normal resistor withstands. So, you may have to put per 1000 volt to 4 resistors in series, so that the voltage can be shared. Now, in this case this will work all right only if this transistor whatever we have is having a voltage rating of more than 1000 volt, because we will soon see that in case if this is short circuited, we want to make sure that this is not going bad. For that we add the short circuit protection circuit, like for example, we put the resistance here. So, whatever current that is flowing through that will develop voltage across this. So, to protect, give a short circuit protection, we add the transistor here and then connect to this. So, this transistor now protects this transistor from short circuit protection, from short circuit. What really happens is when the short circuited, the output is short circuited, then large current flows through this. So, as soon as the voltage across this exceeds more than 0.6, that is then the base emitter voltage exceeds more than 0.6, that makes this transistor to connect, the current flows through this. So, whatever current that is coming here, that actually goes through this. So, the current flows through this, the current flowing through that will develop a voltage across that will reduce the voltage at this point. So, voltage at this point will come down automatically to make sure that the voltage at this point comes down. So, as more current goes. So, eventually if further current goes up, then this conducts further and make this voltage come down further. So, eventually if this is 0 volt and this will sit at 0.6 and this will come to 1.2 volt. So, current through this will go such that this voltage is down to 1.2 volt, that happens automatically. That is how short circuit protection is activated. So, in that case if you see when it is output is shorted, this is 0 volt, and if it is a 1000 volt regulator, this definitely will be more than 1000 volt, it may be 1100 volt. That means this transistor has to withstand 1100 volt, that VCE breakdown voltage should be more than 1100 volt, then only the circuit will work. So, we need to have a transistor which has sufficiently high beta, so that the base current is small, and then it is able to withstand 1100 volt. Now, instead of looking for such a transistor, which is difficult to get, one can have transistors connected in series to solve this problem. Now, what can be done is, if I want to connect the transistors in series, we can do in the following manner. Like I can take, because we want to make say 350 volt transistors, if I have, I can put 4 of them in series. So, that I will get 1000 each one 350 volt, that will make 1150 volt withstand capability. So, I can put 4 transistors in series like this. Now, when I put transistors, I put on Darlington also, so that the base current becomes small. So, this also 300 volt only, each one is only 300 volt. So, I connect this each one on Darlington and get the output. So, this is our unregulated DC here. So, you have the negligible base current, because if you need, we can put one more Darlington also if you want to reduce the base current here. So, essentially we have to have a Darlington pair arrangement such that the base current is negligible. This is essential for this design to be successful. So, what I can do is, now I can add resistance equal values. Then, for example, in this case our regulator transistor can be this. If necessary, this also can be made parallel. Right now, I will not look into it, because this is only low power, 1000 volt low power transistors are available, it is not a problem. So, this can be connected to the error amplifier. and the output we can connect to this, and the minus voltage is connected to V reference. So, that actually becomes V output. Now, if you see the working of this, we have connected the transistors in series to make sure that they share the voltage here, because we can use low voltage transistors many in series like this. Any number of transistors can be configured in series in the same format. So, here for example, we have put these resistors equal. So, you have all these resistors are equal values. Now, assuming that these currents are negligible, that you have I1, I2, I3 and I4. So, if I1, 2, I4 are negligible, this is very important, negligible compared to I is the current that is flowing here, that is the current that is flowing this and the current that is flowing here, they will compare to I. Compared to this current, these I1, I2, I3, I4 are negligible. That is a must for this design to be successful. So, if that is the case, then we know that the current flowing here current flowing voltage across this and voltage across this, voltage across this and voltage across this will be equal, because are equal and same current is flowing, because I1, I2, I3 are negligible. So, voltage across this all four resistors will be equal, and voltage across this nothing but the base emitter voltage of this transistor, that is collector emitter voltage of this transistor, because base emitter voltage only 0.6. So, neglecting that, the voltage across this is nothing but voltage across this transistor. So, that means the voltage across each transistor is identical. So, the total voltage 1000 volt, even if it is there, it is shared by the 4 transistors. So, voltage across any transistor will not go beyond 300 volt or 350 volt. So, we can use many transistors in series, so that the voltage is shared. So, in this case, if the output voltage goes high and then this voltage goes high, then this voltage goes high, this conducts more. When this conducts more, then more current flows through this. When more current flows through this, voltage across this increases, across each transistor increases, so that output voltage decreases. So, this way the regulator, the transistors can be connected in series. This is very important when we are dealing with high voltage. Like this, any number of transistors can be connected in series, and then one can develop a very high voltage power supply. Of course, even the transistor can be connected in series as well as parallel. Even this transistor also can be connected in series in the same manner here if required, but normally for low power you get high voltage transistors available easily. For example, BU208 gives you 1000 volt rating, so one can use this. So, we had seen how to connect the transistor in series and parallel. So, we connect the transistor in series to boost the voltage. So, connect the transistors in series to boost the voltage handling capacity. Voltage handling capacity of the circuit. Individual transistors are still handling only low voltage, but now we can construct a circuit which can handle much higher voltage. Then connect the transistors, in parallel to boost the current handling capacity of the transistors. current handling capacity of the transistors. Or it can also be that is, we can also say connect the transistors in series connect the transistors in series to reduce the heat dissipation. Transistors in parallel, sorry, connect the transistors in parallel to reduce the heat dissipation in one single transistor. This is essential to see that the junction temperature is kept at junction is kept at low temperature. That is why we connect the transistors in parallel. So, one can connect the transistors in series or parallel without violating its working concept, working principle, and then we can derive the advantage of increasing the power or increasing the voltage rating. Now, let us see next how to use MOSFET effectively in analog circuits, because we had seen earlier how to use the MOSFET for switching applications, because we had seen both how to use the transistor as well as MOSFET for switching applications. Let us see how to use the MOSFET in linear supply. So, that will give an idea of the usage of MOSFET, and the usage of MOSFET is now nowadays more and more in linear supply, because the MOSFET had advantage that voltage drop across that can be very small, not like transistors that for example, if you take 3055, it needs minimum of 3 volt across base and emitter when I current is flowing, whereas MOSFET even with 10 ampere current we will have only about 40-50 millivolt drop across that. So, low dropout regulators are being developed using MOSFETs. So, the MOSFETs are nowadays finding its way in linear power supply, particularly low dropout regulators. Let us see how to make a low dropout regulators using a power MOSFETs. So, in this case what you do is we will have our conventional circuit, we have a transformer, then we have our rectifier circuit, then we will put our filter here. So, that gives you unregulated DC at this point. So, we got unregulated DC. Now, that is to be regulated. Only thing we do is we will not put our transistor. Instead of that, I will use a MOSFET, I will use a P channel, I will use a MOSFET here. Now, error amplifier, it have an error amplifier here. The output is there. The same concept can be used. What we have done in the linear regulator is the output, and then we have a capacitor here. That part remains same, and then we have error amplifier plus and minus. So, this can be given to the feedback, and we have a. So, we had used here the Zener diode of 5 volt. Assume it is a 5 volt Zener, and we have biased the Zener using this resistor. So, the whatever voltage is here, that drives the current through this, and we have to keep the resistance such that the enough current is flowing through the Zener. This we had discussed earlier. So, eventually you get 5 volt here, and you have a output at this point. So, part of the output is now compared. Assume that we have here both resistances are 10K, similar to what we have discussed. So, voltage across this 5 volt, and then voltage across this also will be voltage across 5 volt, then voltage across this also will be 5 volt. So, you will get 10 volt at the output. So, to get that we have to complete the circuit. So, what I do is this is N channel MOSFET. So, I connect this to this. Now, that completes the regulator part. Now, what is happening is, suppose if the output voltage goes high, then this voltage goes high. If this goes high, then this voltage comes down, and that will make this voltage come down. But then there is one difference between the transistor and the MOSFET. In the case of transistor, the voltage difference between this and this terminal, that in this case in transistor it was base and this was emitter. Here in this MOSFET it is a gate and this is a source, and in transistor we need only 0.6 volt difference for this to conduct, whereas in this MOSFET we need almost about 10 volt difference in power MOSFET. For the transistor to conduct MOSFET to conduct heavily, we need about 10 volt difference between gate and source. So, we have the gate here and then the source. So, that means if I want, for example, 10 volt here, then if this is sitting output is sitting at 10 volt, then this has to go to 20 volt, then only you will get the 10 volt difference. Then only the transistor will get into a deep conduction mode, otherwise it will not be conducting heavily, and then it will not able to sustain a heavy load current. So, you need large difference between gate and source. This is one of the drawback of the MOSFET, because if it is a transistor, one can switch on and off with 0.6 volt, whereas MOSFET needs extra gate and source voltage, which may not be available in low voltage instruments. That is why the MOSFET is not extensively used in low voltage power supplies. Now, in this case all that required is I had to give a supply voltage here much excess much higher than the 10 volt, at least 20 volt power supply required. So, in normal case what we do is the supply for this normally connected to this itself. Normally we connect this fellow to the input itself, and that will not work in the case of MOSFET actually. So, what can be done is that we can have another supply. One easiest thing would be can have another winding which may be 20 volt or 25 volt higher voltage, that can be connected to this. So, that this is 25 volt available, and that can easily give 20 volt here, and then a 20 volt here can easily give 10 volt, and this need not be more than to get 10 volt, all that needed is at this point even 10.5 volt is enough, because at low voltage you get MOSFETs with 5 milliohm channel resistance. For example, even if it is 10 ampere current, 5 milliohm 10 milliohm resistance will need 10 milliohm into 10 ampere will give only 100 millivolt drop. So, up to 100 millivolt down the MOSFET can work. This is the basic principle behind the low dropout regulators. So, only thing is that you need additional supply to boost this thing, and even this supply can be achieved in very many different ways. Of course, if you have a transistor based supply, this is more convenient way of obtaining the high voltage supply that is required for the for this error amplifier. This is actually gives very low dropout, and the advantage with the MOSFET is that extra voltage that was lost in the transistor is no more there, and one can easily work very close voltages. Particularly this is well suited for regulating the battery voltages, because here you will have a ripple and then the mains voltage change also will be high, and the advantage that you gain is not very much. But if you are operating a battery based equipment, or already regulated voltage supposed to be regulated further, then this kind of low dropout regulator is very much of use. So, for example, if I have a battery, if I want to make battery voltage to be regulated, because battery voltage is not going to change much, in that case I can go for this low dropout regulator. Then this output can be now compared with the reference. So, you got V reference voltage, and the power for this can be given from here. Now, only question comes that if what is the power supply voltage I have to give, because I need to give supply voltage much higher than if I connect this chap to this, the output of error amplifier to the MOSFET's gate. So, I can connect this one to the gate and source. So, if I need 10 volt here, and if this is 12 volt battery, then if you get 10 volt, then I need around 20 volt at this point, and this need to go up to 20 volt. So, 20 volt cannot be obtained from this 12 volt I cannot connect here to get 20 volt. So, there is no possibility of now operating unless I give this one 20 volt. Of course, you can obtain 20 volt from this by using a small DC-DC converter, because or this voltage can be boosted in a simpler way. For example, simple booster circuit I can show you in this case. So, I remove this. For example, I can do this in a simpler boost circuit, which only very low power is required. Now, one possibility is we can also go for a small oscillator circuit and then produce, because this needs very small power only. So, I can have a simple oscillator circuit, and which has AC oscillations, and that can have a transformer to boost the voltage to 20 volt, because we need only very small power, and that 20 volt can be given to this. So, for example, a simple oscillator will do, because we need only a very small power to boost this. So, this kind of low dropout regulators are popular. Now, I can show you one of the oscillator circuit to go with this. For example, simple Hartley oscillator circuit will do for this purpose. So, we already discussed about the Hartley oscillator circuit. So, we can have, for example, 12 volt, because the power level what is required is very small. So, in that case one can use this kind of oscillator circuit and have this, and you can have a secondary which is stepped up, and this can be used to rectify and get a DC voltage. Having a small resistance helps here, and this can go 20 volt, and a few milliampere current can be easily achieved in this circuit. This is basically Hartley oscillator circuit, which again we have discussed earlier. So, the Hartley oscillator can be also used to increase the to power the error amplifier, because error amplifier needs much higher voltage than the battery voltage. So, the battery voltage is fed here, and you got higher voltage at this point. So, the this way the MOSFET can be used in the place of transistor, and the MOSFET gives you better performance, because the voltage drop across the MOSFET is smaller compared to the transistor, and then the gate current is very small. But then the disadvantage of having higher gate voltage compared to the source is a disadvantage there with MOSFET, which was not there in the transistor. Of course, that can be handled by using a oscillator circuit like this. So, now let us see how to provide a short circuit protection for MOSFET, because MOSFET is used in many switching applications as well. Like for example, I may be using a MOSFET to switch high loads. For example, I may have a high voltage, for example 100 volt, and then I have a load, and then I want instead of transistor I want to use the MOSFET to switch this. So, I use this. So, here for example, I give a voltage with respect to ground, say I have 15 volt, I give say 15 volt DC, then the MOSFET is on, and if I give 0 volt to this, for example, I remove this and then connect to 0, then the MOSFET actually goes off. So, I can make it on off using the applying the gate voltage, that if 15 volt is given, MOSFET goes on and the load conducts, and if I give 0 volt, then MOSFET goes off and then no power is delivered into the load. So, one can use the MOSFET to make it MOSFET as a switch rather than the transistor. However, in this case we had give a protection for MOSFET, because if you take this load, in case if the load is short circuited, and assume that I had given a voltage to this MOSFET to make it on, I connected this 15 volt, then the MOSFET is on, and in case if it is short circuited, then a huge current flows through that and then the MOSFET goes bad. So, it is essential that we give a short circuit protection to the MOSFET. So, how to provide a short circuit protection is one of the important problem. So, short circuit protection for MOSFET. Now, in the case of transistor, we have done the short circuit protection very easily. The MOSFET short circuit protection is little cumbersome, and also we had to see how to protect without giving too much of power. Now, the same logic what we had used in the transistor can also be used first in the MOSFET. For example, in the case of transistor, what we had done was, if this load, for example 100 volt, then short circuit protection is provided like this. We have done and connected this. So, our drive voltage was diverted out. For example, this is what we have done to protect the transistor from short circuit. In this case, if this load is short circuited, for example, if there is a short circuit here, then I current goes through that. Then if the voltage at this point goes more than 0.6, it goes more than 0.6, then this transistor start conducting, and then whatever current is flowing, now this conduction current actually comes from here. So, large current flows through this, that makes this voltage to decrease, and that makes this voltage to decrease, and the conduction here also decreases. So, eventually, for example, if I put here 1 ohm resistance, then voltage at this point cannot go more than 0.6. That means current through this cannot be more than 0.6 amps, because voltage at the base emitter cannot go more than 0.6. So, VBE is equal to 0.6 volt, that is equal to I into R, that is this R. So, if R is 1 ohm, that I into 1 ohm. So, 0.6 comes as 1 into I. So, the current I comes as 0.6 amps. So, in this case, even if short circuit, current will not go beyond 0.6 ampere. So, short circuit current is limited to 0.6 ampere. short circuit current is limited to 0.6 amps. Now, the same technique can be used even in the MOSFET. The MOSFET, what can be done is that if I take the MOSFET case, I put the resistance to ground, then assume this is the load and this is the supply voltage, the drive voltage here. Now, the MOSFET, assume that I connected through a resistance to the gate, then the same circuit works all right. Now, from the earlier discussion that we can quickly understand, suppose if I have 1 ohm here and this is the base emitter voltage cannot go more than 0.6. So, if the current goes more than 0.6 amps, this voltage will go. This voltage will go beyond 0.6 volt. Once it goes beyond 0.6, the transistor will be start conducting, and this would be start conducting, and then this voltage will be decreasing. As this voltage decreases, the conduction also will decrease, and eventually the current will be limited such that this is sitting at 0.6, and then this will be sitting at a few volts such that 0.6 ampere current is flowing. The same technique can be used, but then in both cases that we have a issue that here that the heat dissipation in this case, if it is 100 volt and if it is a short circuit 0.6 ampere going through that, then heat dissipation will be 100 volt into 0.6 amps, that will be 60 watts of power dissipation will be occurring, and this is true in transistor also. But then one can actually avoid the 60 watt power dissipation if we can shut down the transistor once we know that short circuit had occurred. Now, that is also can be done in the MOSFET. Now, one can think of the following type of circuit which used invariably in the switch mode power supplies. What can be done is that you can have a load for the MOSFET. Now, I can retain this because this is very quick in acting. I can have a load here, then connect to the source which is say 100 volt. Then our regular transistor also can be put here, that our short circuit linear power supply stub that we can connect here, and then I can connect the drive part of the voltage. Okay, this is connected here and that is connected to ground. So, I can put the resistance, say this is R, this is load, this is R sense. So, this is the MOSFET which is supposed to be protected against the short circuit. In this case, if the short occurs, then current will go high in this, that will increase the voltage at this point. Then immediately this transistor will conduct, and then more current will flow through this, and that will make the voltage at this point reduce, and that will reduce the current. So, eventually voltage at this point will be limited to 0.6 volt. So, 0.6 divided by this resistance will be the current that will be flowing. Now, we are trying to remove how to avoid the power dissipation in this, because if I put 1 ohm, then as we said, then current is 0.6 ampere only, can go not more than that. But then if this is short, the entire 100 volt is here, 100 volt and 0.6 ampere will give you 60 watt power dissipation, which is very high, and the MOSFET can go bad. To avoid this, one can sense the voltage at this point and then use that information to shut down the transistor. For example, when the MOSFET is fully on, for example, when this is transistor is not there, and if I am switching it on, then voltage across the device will be only few millivolt. For example, if it is 1 ampere current and if I use a MOSFET of 10 milliohm resistance, channel resistance, then you will have only 10 or 20 millivolt, 10 millivolt drop only there. So, and then you have some voltage drop across this depending upon the resistance. So, voltage at this point will be always voltage at this point is always lower. So, if it goes more than 2 volt, that means that this MOSFET has been taken to linear region. So, that means by sensing this voltage one can identify whether the MOSFET was taken to linear region by the short circuit protection or not. So, because when this transistor is activated, because of the high current, when this transistor is activated, this voltage is decreasing and the MOSFET is taken to a linear region, and then voltage at this point goes up much more than 2 volt. So, I can say with the voltage at this point goes more than 2 volt, the MOSFET is taken to a higher level. So, one can sense this voltage, and if the voltage is higher than the prescribed amount, say 2 volt, that I can set the reference. So, when the voltage goes higher than that, then output goes high, and then one can actually remove at the source itself the source drive itself can be removed. So, once the drive is removed, then automatically no switching takes place and MOSFET goes off. Of course, we have to have a latch such that once it goes high, that it never comes back again. So, that kind of arrangement can be done. This kind of thing is done in switch mode power supply, so that the MOSFET is not get damaged, and this, in that case, this will act as a quick current limiter, because if I use without this, if I use only this technique, for example, I had put a latch here. So, if I put this one, for example, I put a latch here, latch I put and give it to the shutdown terminal of this. Now, if without this, for example, if I not used the this arrangement and if I short, then this voltage will go high and it will latch and then it will pull down the supply. For example, without this, if the short circuit occurs, this voltage goes high and then this goes high and latches and then permanently pulls down this voltage. But then this has its own slew rate, this has its own slew rate, and it takes time to shut down. By that time, the current in this MOSFET would have been raised to much higher level and would have destroyed the MOSFET. So, this arrangement helps you to limit the current during this time interval, that is delayed time, because when the when short circuit occurs, the voltage goes high, but then shutdown takes 1 or 2 microsecond. In 1 or 2 microsecond, the current would have been ramped up very high and would have damaged this. So, if I have this plus this arrangement, and this arrangement actually limits the current during that 2 microsecond, such that current will not go anywhere more than 0.6 and current will not go more than 0.6 ampere. So, the current is limited to 0.6 ampere, and then this takes over and switches off the source itself, and that way the MOSFET can be protected without damage. So, this combination of shutdown plus current limiting is a useful technique in MOSFET power protection. Now, we can see this kind of circuit in detail probably in the next class, how to provide a latch and do this. I can take one switch mode power supply example and explain how the how one can protect a MOSFET against short circuit. There are many publications available in this topic. One can see that. One can see these applications in many published journals. So, in this class we had seen how to use the transistors in parallel to boost the power, then how to use the transistor in series to boost the voltage. How to design these two circuits we had seen, and also shown you how to use the MOSFET as a switch, and then how to use the MOSFET in the linear power supply in low dropout regulators, and also I had shown you how to protect a MOSFET from the short circuit protection. So, we will see more about this in the next class. Thank you.